Okay, part two. Let's get on to some new stuff. This is a new and special kind of group. So I'm going to start out with G being a group, right? So G is a set containing some elements, and there is some kind of operation that combines those elements and gets me back a new element, right? Seen that already. I'm going to call G a cyclic group so long as G follows two rules. Number one, G has to have some element A, right? I'll call A my element. And A has to have finite order. So you can check the previous part of this lecture for more on that. So some finite combination of A's gets me back to the identity element in G. That's rule number one. Rule number two, every element of G is some combination of A's, right? So if I'm looking at addition, right, I'll just call A plus A 2A, I'll call A plus A plus A 3A, and so on, right? So everything can be represented as some n times A if G uses addition as its operation. If G uses multiplication as its operation, I'd probably use exponents instead, right? So I'd look at A to the power n, say that's A times A times A times A, n copies of A, throw them all together. Or maybe I use some other strange operation, and I'll call that star just to stay generic. I'm looking at n copies of A all put together with my operation star. And so every single element of a cyclic group has to be written out as one of these formulas, depending on what operation we are looking at. Now, cyclic groups are really cool and very easy, in my mind, to work with because cyclic groups are automatically abelian. Everything is just a bunch of A's put together, right? So it doesn't actually matter what order I put them in together, right? Every copy of A, I can just shuffle that around. They're all the same to each other. So fortunately, I'm back in the position where I don't need to worry about what order I'm doing, like, oh, A star B or B star A. That will not matter for a cyclic group. The other nice thing about cyclic groups is that they are finite. So having a finite abelian group is a very nice thing. There's a theorem about that I hope to have probably on Friday's lecture. But for right now, let's just think about what we could have in a cyclic group. Now, these seem kind of strange, maybe. Yeah, I think all of group theory asks us to consider very strange algebraic circumstances. But we've actually been working with cyclic groups from the very beginning of this course, right? So have we seen these before? Every single group Z mod NZ is a cyclic group under addition, right? So this group consists of all the residues mod n, and we've been using the set 0, 1, 2, 3, 4, up to n minus 1, and then say that n wraps around, n is the same as 0 mod n. Those are my residues. And I claim that this is cyclic because every single residue in that set is just some combination of, can you figure it out? Every residue is some combination of ones. Because what is 2 but 2 ones? What is 3 but 3 ones? What is 4 but 4 ones? Even as residues, those kind of easy equations still work. So every single element of this group is some combination of ones, which means that this is a cyclic group. Now, are these all of the cyclic groups we've seen? Well, there's a bit of a philosophical question there. We'll leave that aside for right now. In fact, there are more groups that we have seen that are also cyclic. So here is a theorem. If P is a prime number then Z mod PZ cross, or Z mod PZ times, or you can say the units modulo P. Those all mean the same thing. This set will always be a cyclic group as long as we're working modulo a prime. So this is something I mentioned back before our mid-semester break. My multiplicative group is always going to be cyclic. So if you think about this, what I'm saying is that to a group theorist, Z mod PZ times, under multiplication, that's a group, and Z mod P minus 1Z, that is also a group, and that is a group under addition. A group theorist would say that those groups are basically the same, right? I know that there's P minus 1 elements in this group. That's how many units I have mod a prime. So these are both cyclic groups. They're the same size, so they should be behaving the same as well. That's a pretty abstract thought, so let me be more concrete. I'll pick an example. I'll take a prime to be 11 is my prime number. And I claim that every non-zero residue, mod 11, can be written as a power of 2. And that is because 2 has order 11, 2 has order 10 in this multiplicative group. Let's actually calculate it out. 2 squared is 4, right? 4 times 2 is 8. 8 times 2 is 16, but that wraps around to 5. 5 times 2 is 10. 10 times 2 is 20, but that wraps around to 9. 9 times 2 wraps around to 7. 7 times 2 wraps around to 3. 3 times 2 is 6. And 6 times 2 is 12, which wraps around to 1. So that is my identity element. The smallest power of 2 to give me the identity element is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? 2 to the power 10 is 1 modulo 11. Since that list has every single residue in here, that means this group is cyclic, right? Every single one of these residues is just some power of 2. So the vocabulary I would use here, previously I've said that 2 is a primitive root of 11. That is particular vocabulary when we are working in modular arithmetic. Primitive root just means that every element of this set is some power of 2. 2 has order 10. Those are equivalent statements. More broadly, in stranger and more diverse groups, I would say that 2 generates this group, Z mod 11 Z times. 2 generates the group of units, mod 11. Okay, so this is going to be our key for understanding why the group of units behaves like Z mod 10. So over here on the very left side, I've got my units modulo 11, right? And I've written them out in the order they appeared on the previous slide. So here's 2 to the first, 2 to the second, 2 to the third, and so on. Each one of these elements under multiplication is going to follow the same rules as do the exponents of the 2's under addition mod 10, right? So what is 8 times 10? That is 80. What does that reduce to? Mod 11. Well, let's just say that's 2 to the third times 2 to the fifth. Put those together. That's got to be 2 to the power 8, which is 3 mod 11. Is it the case that 80 is congruent to 3 mod 11? So here's my 80. Mod out by 11, I get 3. I can do this for any pair of these things. If I want to take 9 times 6, that is the same as 2 to the 6 times 2 to the 9. 6 plus 9 is 15, but that's just 5 mod 10. So I go back to my 2 mod 5, 2 to the 5th power, and I've got to get 10 out of that. Is it the case that 9 times 6, that's 54, does that get me 5 mod 11, or 10 mod 11, excuse me? Yes, it does. So I can calculate my multiplication on the left column here by instead going to the corresponding addition on the right-hand column. Both of these are cyclic groups, right? So everything over here is just some copies of 1 put together. I'll say that 1 plus 1 plus 1 gives me 3. Over here, everything is some number of copies of 2 put together. I'll say that 2 times 2 times 2 is 8. But really, these are going to behave in the same way. It's just that on my left side universe, I'm using multiplication. On my right side universe, I'm using addition. Both of these are cyclic groups. Okay, right. So that is a lot to digest. I think that kind of stuff is fascinating. The big thing that I want to get out of this portion of the lecture is just that cyclic groups exist. They're very nice to work with because they are finite. Everything is equal to some combinations of the generator, A, and they have this notation where I'll just say that G is equal to bracket A bracket. So this will work for any cyclic group. This leads into my final piece for today, which is on subgroups, and I hope to see you in just a minute.